I'm on a mission to make an unpickable lock. The lock I've made has a huge problem, and I'm going to solve that today. The design I'm working with separates the setting from the testing of pins. To do this, wafers are utilized to lock in the height of the pin stack. The second shear line performs the testing operation. This architecture, however, limits the core rotation to one direction. When you put your key in your door, you turn it one way to lock it and the other to unlock it. So, as a handful of people noticed, how do you lock this lock? This problem is not unique to this design. Disc detainer locks, such as the one in this padlock, have the same problem originating from a similar architectural constraint. So all we have to do is see what they do for their front door locks and copy it. Where are they? Outside of a few very expensive ASA Abloy locks and the legendary Boley Rotocera, there's really nothing I can find. The Abloy locks work off of a quirk unique to disc detainer locks, while the Boley solves the problem by melting your brain and moving axially. Neither of these solutions particularly fit this design, so we'll have to look elsewhere. Restating the problem in simple terms, while the core is not capable of rotating relative to the shell in the locking direction, all we need is the tailpiece at the back to move in the locking direction. So we could just rotate the entire lock. So I realized something. We rotate locks all the time in regular locking doorknobs. Basically, we just need to put the lock inside of a knob, and then instead of retracting the bolt when you rotate it, it needs to extend it. Since the lock will be moved further from the door, that will make it more susceptible to physical attacks. When looking at these physical attacks, many seek to break the area around the strike plate or the area of the door around the deadbolt. Combating these attacks relies more on the quality of the door and the door frame rather than the lock itself, so they're out of scope here. But there are physical attacks that do rely on attacking the lock directly. The one that's particularly troubling, given the fact that the lock will be protruding from the door, is an attack that seeks to expose the back of the deadbolt. And I'd like to demonstrate what this attack looks like. I've tightened down the housing as much as I can, but it's not going to matter because the housing has no way to react to the loads that I'm about to apply to this. So the first step is to strike the top of the housing. Then I'm going to insert a screwdriver. And I'm just going to find the top of the deadbolt and I'm going to walk it back. And there you go. To mitigate the effectivity of these attacks, the shape and load paths must be evaluated. To start off, let's see where this housing tack went wrong. The front and back housing sandwiched the door with preload from two fasteners represented by this rubber band here, and depicted on this free body diagram as F sub F. The door, of course, reacts this force with normal force in the static scenario. If a load is applied as such, the force is reacted through the friction at the interface. In the static scenario, the static force of friction is only dependent on the normal force and the static coefficient. And since the normal force is only dependent on the preload of the fastener, the equation can be written as such. So as we can see, the only thing preventing this from sliding is the preload on the fastener. And if this equation is ever not true, then we get into a dynamic scenario, which we saw in the demonstration. Looking at the moments applied, the relatively short lever arm and wide base can adequately dissipate the loads. I do have some concern when we go to a knob and this lever arm becomes a lot longer. So we'll want to work to minimize that length. Additionally, we can look to beef up this contact interface here to mitigate stress. To transmit loads and allow for a smooth operation of the return spring, I will be using a bearing. Given the directional nature of the expected forces, I did look into roller and tapered roller bearings. However, the cost and size weren't quite there. I have gone back and forth on how to integrate these bearings into the larger mechanical topology, but this is what I have. The knob rests on the bearing, allowing it to transmit the axial pushing forces and the radial loads. The bearing is also captivated on the other side by a low profile snap ring that takes up the pulling forces. On the inside of the bearing, the The static center is there to transmit radial and axial load in the pulling direction. It is hollow in the middle to allow clearance for a spring around the cap. The center part transmits those loads back to the door through another part that also takes up the axial load from the bearing in the pushing direction. With the design done, I placed an order with today's sponsor, PCBWay. PCBWay is more than just a PCB fabrication assembly shop. They do 3D printing, sheet metal fabrication, injection molding, and, important to this video, CNC machining. These parts just came in from PCBWay and they turned out great, and significantly cheaper than other services I've used in the past. Drop your parts in their website for an automated quote and see how much it could save you. Thanks again to PCBWay for sponsoring this video. So we haven't talked too much about locks in this lock video. I have made some improvements to the old design here. One of them is that it's a little bit thinner, as you can see. And also I've moved the clocking position from the back of the lock towards the front to try to reduce some potential moments and binding that could be happening in there. Got some notches here to help it fit in the enclosure a little bit better. And a very nice dovetail at the top so the electrical tape can finally go away. And then as far as the pinning goes, I've got this pinned up. I've got 2 impact arrest stacks and then 1 steel driver pin and then a couple different force springs in here. And all of that is to combat the impact attack, which we saw was successful in the last video. And of course, we'll be trying that again today in the door. So with it all pinned up, you can see that works. So let's get this thing assembled. So I've got the lock here with the torsion spring. I'm going to drop that down into the knob. And I'm going to bring over the bearing. Drop that in. And all of this gets held in place with a snap ring. And then the base flange gets mounted onto here. All right, let's look at the functionality here. I can insert the key, and then I can rotate it to unlock the door. Then, of course, I can use the key to lock the door as well. This has another feature because of the knob design. You can lock the door using the knob. Currently has a bit of a clocking problem, but something I'll have to fix, but it's basically there. All right, I've got the door closed and locked here, and let's start out with some non-destructive attacks. First up, we have a wave rake and a 40 thou turner, and I'm just going to try to rake this open. And there we have a very deep false set, which is the testing occurring basically. Let's try that again. And realistically, we'll be here till the end of time trying this one. All right, so we keep dropping into this false set, which is the entire design of this lock. Basically, the pin stacks are being tested at this height, and they're failing. All right, this deep false set brings up the next attack I want to try, and that is walking back the deadbolt. Basically, the concern is that because the false set is so deep, it could potentially unlock the deadbolt and allow it to be retracted manually. And it is not working. Just kind of scraping material off the top here. Let's use the key and figure out where in the rotation the unlock happens. All right, so we're just looking for movement on the deadbolt. It's gonna be very hard for the camera to see, but we've got movement right here. So that's well past 90 into the maybe 120 region. So we got a pretty big margin from that attack being successful. All right, next up we have a highly requested tool. That is the Lishi tool. The Lishi tool is a great 2-in-1 turner and pick that gives you great visual feedback of what's going on inside the lock. So let's try this thing out. So we can feel around. I can feel the various pin stacks here. Having a little bit of resistance on a few of them. There's a lot of the wafers and the two shear lines give a lot of feedback in this lock. But we're able to push basically whatever pin stack we want around here. But the issue here is that just the act of inserting the Lishi tool, if I try to tension the lock, which is one of the two things that you need to pick the lock, the tension and the access, if I try to tension it, you will see that we immediately fall into that false set. And that's because the Lishi tool has raised all of the pin stacks just slightly to the first level. So, but we could go in here and we could, in pin stack 1, we could set it to some level, let's say 4, and then we could try to turn the lock, and you can see that it has dropped into the false set and is not opening. But the issue here is, I'm not going to go back to top dead center, is you can see, we're at 4 here, but if you go to these other pin stacks, they're all going to be at 1, right? And maybe in theory you could use this to brute force, but the issue is the pick only lands on 1 pin stack at a time. And of course, brute force is the ultimate thing you want to throw at an attacker because it's so hard to do. So maybe you could do it with this. I find it very hard to set 1 pin and then set the next one. Like the second you've set one and you've moved on to the next one, it resets. Basically, you would need a Lishi tool that has 1 pick for each pin stack, and then that would be enough to help you brute force the lock. Brute forcing it is obviously going to be quite the ordeal because you'll have to turn it like this every single time. There's a YouTuber called Sparks and Code that's out there that has a pick which is robotic, and it has the ability to manipulate all of the pins independently, and something like that would probably be the best shot at single pin picking this thing without some kind of other interference. Now moving on to the attack that I want to spend more time on. That is the impact attack from last time. Essentially, we move the lock into the full set position, and then the theory is we strike the lock, and then this causes the driver and master pin to jump, and the driver pin can get over the shear line and we can get an unlock. I'm going to use this hook to lift all of the pin stacks to the highest position. But I do have those impact arrest stacks kind of in my way. So using just this hook, I'm not able to get them all the way to the highest position. I can only get to the second highest position because of those stacks. All right, so my plan is I'm going to insert this 40 thou turning tool, and I'm just going to impact the lock. I'm going to start on the top. We'll see how that goes. Maybe go to the bottom. Here we go. I'm trying different things with the tension there, trying to get it to, basically we need the pins to be able to fly up and then we need to catch them. So I'm trying to loose light tension and then heavy tension, light tension. I don't know. Has begun to turn a little bit more. It's nearing 90 maybe. I'm not sure if that is the pin stacks though. I'm kind of wondering if something in there is sliding a little bit. Let's keep it up. And we got an open. Oh my God. All right, I'm gonna gut this lock and let's see what's going on in there. All right, here's what I found in the lock. I've got the core, mid-core, and Bible sections in their own parts of the tray here. I accidentally allowed these to combine, so just ignore that in the core and mid-core for pin stacks 1, 2, and 3. But I think a better way to look at this is on the computer. Here I've recreated what I believe happened in the lock. Looking at the 2 rear pin stacks, it does appear that the pins were only able to be lifted to the second highest cut due to the impact arrest stack in chamber 3. I'd also selected chamber 5 to be an impact arrest stack, but it was a 2-cut location. And of course, the second highest location is the 2-cut. Stack 4 was also a 2-cut, so it was raised to the opening height. This left only pin stacks 1, 2, and 3 to keep the lock from opening. When the lock was impacted, the pins would fly up over and over. Then, with the right amount of tension, impulse, and rolling of the dice, the pins were able to line up at the shear line. The momentum transfer seems to be quite good here, exemplified by the fact that in the final configuration, pin stacks 1, 2, and 3 all finished with wafers above the shear line. This means the pins jumped up at least 70 thou. There's also likely some kind of binding order at play here that could get the pins to this state beyond random happenstance. Regardless, it is clear that these impact arrest stacks are insufficient for dealing with this attack. We need another course of action. As many of you pointed out, and is painfully obvious by this point, we need a physical hard stop to prevent the pins from coming up above that shear line. So once again, we're trying to keep the master pin from being able to go over the top of this secondary shear line. As far as limiting it goes, perhaps we could have a slender pin in the center of the spring, or maybe a sleeve or a shoulder machined into the body of the lock. But all these solutions add parts or more complicated machining operations when every compression spring comes with a built-in hard stop. It is called the spring's solid height. When the spring is compressed to the point where all the coils touch, it starts behaving like a solid in compression. So long as this does not yield the material, it will be suitable for our purpose. All right, so the distance we need to prevent this thing from jumping is 23 thou. So I measured the solid height of the springs that I'm using. Then I brought the pin stack up to its highest level and measured down in from the top to see how much free space is at the top. And then I subtracted the 2 numbers and filled in the rest of the space with pins. So to be confident that this will actually work, I need to know that it's not going to jump, even on a single pin stack like I have in this lock. All the rest of the pin stacks are empty except for the watchdog pin. Let's get this thing loaded up and see if we can get it to jump. All right, so I've got the 1-pin lock installed on the door here. Let's see that it works. All right, gonna raise it up to the maximum height. Let's do this thing. I seem to be damaging the door here. Looks like it's loosened up some because the door is caving in. I don't know, just keep trying, I guess. Okay. Oh my God, I sheared them off. So I sheared off both of the M3 standoffs that go through to the thumb turn. So that will need to be fixed. I think that's probably a good stopping point. It performed really well. I got a lot of good hits in, and I'm not sure it's 100% ready. I would love to hear what you have to say in the comments about this idea of limiting the pin height using the spring itself. Anyway, let's go try out some other stuff. Online, there's a lot of emphasis placed on covert attacks. And while resisting them is my goal, I want to make sure this lock can stand up against some brute force. Now, funny enough, the lock was compromised during what I guess I am classifying as a covert attack. Anyway, so the parts that failed were these brass M3 standoffs. You can see here in the unbroken version that the failure occurred right here at this stress concentrator. And from what I've observed, the industry standard is this M5 bolt. This is about 3 times the structural area, plus this is made of steel. So lessons learned here. I figured that loading in the axial direction would be minimal. but this tipping motion we see did it in. As the housing levers off the door, it exerts a moment on the fastener, and we know that fasteners don't do so well in bending. I have no desire to try to drill and tap M5 threaded holes into this 316 stainless, so I put in and torqued 2 new M3 standoffs that I'll be using for the following tests. All right, I've got the lock back here on the door, and I want to test this thing to destruction and see what we can learn. So the first thing I want to do is I want to try to get in here and pry the knob away from the flange, or the flange away from the door, and see if I can get in there, kind of similar to that attack I showed early on. So this lip is doing a pretty good job of keeping me out of the gap between the knob and the base flange. Even if I could stick something in there and pry, I would be prying in the radial direction, which that bearing will be able to take up that load. I don't think there's any luck there. Now, in the back here, I have a feeling if I set this up and I hit it with a hammer, I could probably get this back there. So let's do that. Looks like I can get the door to flex away from the lock a little bit. It's softened up there, of course. But if you remember, there's that flange on the inside that is protecting the top of the deadbolt. So even if I did cut away the material here, I wouldn't be able to access that. I would have to come in from the side here and then up, I guess, and in there's just not going to be much room to maneuver. But get a bigger screwdriver. Now a crowbar might be the right tool for the job here, but I don't have one of those, unfortunately. Seems pretty strong in the axial direction. Of course, there's just those 2 M3 fasteners that are holding this thing in the axial direction. I'm going to upgrade those at some point. So I don't really see the need to test these M3 in this manner any more than this. But let's move on to the next thing. So I figure this is a knob, so why not just try opening it? Turn it in the opening direction. So I've got this pipe wrench on here, so let's just see if I can reef on it and open it. There we go. Sounds like I broke something. There we go. Okay, I've once again sheared off those pins. Let's leave this in here and imagine that was held on better, and because that's the the axial direction. What happens if I turn this thing? So I've got some amount of rotation going on here, and I want to see if I can just get the lock to open because of the false set clocking angle here. Wow, that is tight. So it seems this twisting has already killed the lock. All right, I've taken the lock apart, and you can see that the housing did not fare well in that twisting. So that's something I'm going to need to look into, how that load is transmitted, what other options there might be. I say let's put this thing back together and give it its final send-off. So the lock's now seized up. What are you to do? I do not know why this will not unlock. I think I'm gonna call it good there. Wow, so many brass chips and pieces of pin. All right, let's get this on the table. Okay. Oh, man. Huh. Oh, wow. That is a mess. So looking at the core, you can see that it's been split in half by the drill. And right here, on this side of the lock, there was a hole that contained a pin that indexed with this tongue piece here, which actually actuates the deadbolt. And at some point, that drill drilled out or pushed out that pin in the back here. And when that occurred, that means that the core is no longer attached to the tongue piece. So at that point, once that pin had been drilled out, there's the rotation of the lock doesn't do anything. So if you were attacking this lock, you would need to pull out the pieces of the core through the front of the lock, and then you would need to reach back in here and manipulate this surface right here, or like grab it with tweezers or something. It'll be way back down in there through the center of the lock body. And you'd reach in there and then you'd be able to manipulate that. So it actually turns out that that's kind of a good mechanism for slowing down the drilling, besides, you know, adding pieces of carbide in here or something along those lines. And then on top of that, just the sheer number of pins in here just falling out as the drilling was happening definitely slowed me down. Just the quantity of them. I'd have to go back in over and over and over to clear the pins out as they would come down from the mid-core. Security through obscurity is dead. It's been great taking your feedback and improving the designs of the lock. Bad designs should be fixed, not swept under the rug. I think really good things can be made by working openly and taking criticism. That's why I've decided to open source this design. You can find those files in the description. This was a long one, so thank you for watching.